So now we're going to summarize all this stuff we've been talking about with the graphs between f and f prime and f double prime. So on this one, we're looking at the graph of f, and this is a polynomial. It's degree 4 because it's got 3 terms. The end behavior is the same, so it's going down on both sides. So that's how I know the degree is even. But let's see what conclusions we can make about f prime and f double prime based on the graph of this function. So the first thing we can say about f prime make this, no, that's good. F prime of x, we're doing capital F's here, sorry. F prime of x equals 0 when x equals -4, -2, and 1, because f of x has relative extrema. That's plural for relative maxes and mins. And that occurs at those x values based on the graph. The second thing we can say about f prime is we could say that f prime of x is a cubic function because f of x is a quartic function. The third thing we want to say is the derivative of f is positive on the interval -infinity to -4, and also again on -2 to 1, because f of x is increasing. Right, those are the intervals from here to here, and again from here to here. Those are the two intervals where f of x is increasing. The same can be said about decreasing. We know that the derivative will be negative on -4 to -2, union 1 to infinity, because f of x is decreasing on those intervals. We know that f prime of x, has a negative leading coefficient, because both ends on f of x are going down, like I mentioned before. So that means the leading coefficient on f of x is negative. When we do power rule on that, right, we bring the 4 down and multiply by that coefficient, it's still going to be negative. We know that the derivative changes from negative to positive at x equals -2, because capital F of x has a relative minimum. So we know the derivative changes where there's a relative minimum from negative to positive, and then vice versa. So we'll say that f prime of x changes from positive to negative at x equals -4 and x equals 1 because f of x has a relative maximum, has a relative maximum. Okay, another thing we know is that the derivative f prime of x, well, we're not really positive it has one at this spot, but typically around -3 will have a point of inflection. I have to say that it's not always going to be directly the midpoint of the x of your max and the x of your min. It's not always going to be right in the middle there, but it's somewhere around there. So but just for the purposes of what we're talking about here, the connection between the graph, we know that somewhere in between this maximum and this minimum, there is a point of inflection. So just so we can talk about it a little more easily, we're going to say at -3, there is one, right? So I can say that f prime of x has a relative minimum at x equals -3, excuse me, because f of x changes from concave down to concave up. So point of concavity on the original function means you have a max or a min on f prime. So, I mean, this means it's because, I'll say which means, I'll put a comma here. This just sort of explains why. I know we're only supposed to be talking about f prime, but we know that f double prime changes from negative to positive. That's how we know that f prime has a relative minimum, because its derivative switches from negative to positive. So that's where it would have a minimum. So we're going to kind of do the vice versa thing here. So we'll say that we know that f prime has a relative maximum at, let's see, so somewhere between this max and this min, we have a point of inflection. I'm just going to call it a half. I will make it sort of the midpoint. We'll say there at a half. That's going to be a point of inflection. Notice they're both called point of inflection. It doesn't matter if you're changing from concave up to down or vice versa. We still just call it a point of inflection. It does matter for extrema. Maxes and mins matter if you're changing from increasing, decreasing, or decreasing to increasing. So we're saying f prime has a relative maximum at x equals -1/2 because f of x changes from concave down, from concave up, doing a maximum, concave up to concave down. And that means, just to tell you why we know, because we're only supposed to really talking about f prime, but that means that f double prime was changing from positive to negative. So again, that's why we know there's a maximum on f prime, because its derivative, f double prime, switches from positive to negative. So anytime the derivative switches from positive to negative, that function has a relative maximum. So when I say its derivative, I'm really talking about the second derivative, because I'm talking about the derivative of the derivative. Okay, number 10. What else do we know? We then know that when we know there's a max or a min on the derivative, we're going to know the intervals on which which the derivative is increasing and decreasing. So f prime, the derivative, is increasing on the interval -3 to -1/2 because f of x is concave up and I'll say which means f double prime is positive. So again, we're supposed to be talking about f prime, but I know that the derivative's increasing anytime its derivative is positive. And I know the second derivative is positive anywhere the original is concave up. So, you know, the thinking here can get a little, you can get mixed up a little bit. There's a lot to think about. But hopefully if you're really understanding, you have to be very solid in your thinking of the connection between a function and its derivative. And if you're very good with that, extending to a second derivative and what that means about all three of them, you should be able to kind of think through that whenever you need to for whatever kind of question is presented. Because you can see that this lends itself to asking all types of different questions. If I give you f double prime, I can ask you about f prime, or I can ask you about f, and all the different combinations that I could possibly ask you about. When something's decreasing, when it has a maximum, when it's concave up, where there's a point of inflection. There's all kinds of stuff that you can be asked here. So you really just have to do your best to try to understand the relationship between a function and its derivative and then extend that thinking out to the second derivative. So we also know the vice versa of 10, right? F prime of x is decreasing on -infinity to -3 union -1/2 to infinity because f of x is concave down, and that means that f double prime must have been negative. All right, now let's look at what we can say. That's what we can say about f prime. And I know I talked about f double prime in there a little bit, but it was to help you get an understanding. Conclusions about f double prime. Well, we can say the second derivative equals 0. And I know we're only talking about the second derivative, but I could also say, and I'll say it's 0, and it changes signs, we could say. At any points of inflection, which was x equals, this will be number 1, x equals -3 and x equals -1/2 because f of x has a point of inflection. Or I'll say points of inflection. I'll say it this way. All right, so that's kind of the first thing we think about with second derivatives. We know the second derivative is 0. Because it's a polynomial, I don't have to worry about undefined, okay? But I know the second derivative is 0, and that it also changes signs. So that means it actually has to cross the axis wherever there's a change in concavity. The second thing I know is once I know where the second derivative is 0, I'm going to talk about where the second derivative is positive. It's positive on the interval -3 to -1/2. Right, -3 to -1/2. It's positive there, the second derivative, because f is concave up. So then we're going to do the vice versa. We know that it's negative. The second derivative is negative on the intervals -infinity to -3 and then union negative 1/2 to infinity, because f of x is concave down on those intervals. Wherever the graph is concave down, that means the second derivative was negative. So these blue parts are the spots where it's concave downward, which makes sense. We could also say the second derivative is a quadratic function because f of x is a quartic function. You can also say that it has a negative, let's say with a negative leading coefficient. Because f of x has a negative leading coefficient. That's because these are polynomials, by the way, which polynomial means the powers of x have to be positive and whole numbers, so that when I'm bringing the power down each time I do the derivative, I'm multiplying the coefficient by a positive integer each time. So if the coefficient starts off negative, it's going to remain negative. And this is, again, because they're polynomials. This isn't always the case for all functions, just because I know these are polynomials. All right, so that's what we know. That's all the stuff we can say. It's kind of a summary of what we've been talking about. Let's try it now if we're given the graph of f prime. What could I say about f? So this is what? A cubic function, right? It's got two terms, so that's a cubic. Its trend overall, like over time, it starts low and it trends upward, which means it's got a positive slope, I guess I would say, right? That means its leading coefficient is positive. So it's a cubic with a positive leading coefficient. So conclusions that we can make about f. I could say that f of x, I want to say first that it's well, we're going to take this cubic and add 1 to its power, because it would have been, its original would have been an x to the 4th, right? So f of x is a quartic with a positive leading coefficient. Because, we'll put a because in there, f prime is a cubic with a positive leading coefficient. The next thing I know is that f of x is decreasing on negative infinity to negative 2 union 1 to 3, because f prime of x is negative on these intervals. So I look at the spots where the derivative is below the x-axis, and those are spots where I know f must be decreasing because its derivative is negative. Again, the rate of change idea helps here. If you know the rate of change of a quantity is negative, you know that quantity is going down. If I tell you the rate of change of your bank account is negative, you know the balance in your bank account is going down. Usually happens this time of year. You're buying some Christmas presents and having parties. All right. Number 3. We know that the vice versa, right? So f of x is increasing on the interval -2 to 1 union 3 to infinity because f prime of x is bigger than 0. So if I look at the spots where f prime of x is positive, those are the intervals on which f of x is increasing. Okay, the next thing I know that f of x has a relative minimum at x equals -2 and x equals 3 because f prime of x changes from negative to positive here. So anywhere, this spot where we change from negative to positive, and again here at 3 we change from negative to positive, that's going to be a relative minimum on f. So we're going to do the vice versa. F of x has a relative maximum at x equals 1 because the derivative changes from positive to negative. All right, so that's a spot where the derivative is changing from positive to negative at x equals 1. So if the derivative changes from positive to negative, you know that you have a relative maximum. Number 6. We know that f of x is concave up on the interval -infinity to -1 union 2 to infinity. So it's going to be concave up because the derivative is increasing on those intervals. And that means if the derivative is increasing, that means that f double prime had to be positive. Just like to throw that in there, even though we're making conclusions about f right now. That's the reason we know that. So whenever the derivative's increasing, right? So derivative increasing here, derivative increasing here. Second derivative is positive is what that means, which means f is concave up. So again, just making the connection between first and second, like a function and its derivative is really what this is rooted in. Jumping to the second derivative isn't such a big deal as long as you just know that second derivative just talks about concavity and points of inflection, but the real understanding is the connection between a function and its derivative, and talking about when a function is increasing, the derivative is positive, and those types of things. So we're going to say kind of the vice versa here. So I know that f of x is concave down. On the interval -1 to -2 because f prime of x is decreasing and that means that f double prime must have been negative. Whoops, I should say which means first. Getting ahead of myself because I'm talking before I'm writing it. which means that f double prime must have been negative. So from negative 1 to 2, f of x is decreasing. So that means f is concave down there. Number 8, we can say that f of x has a point of inflection at x equals negative 1 and at x equals 2 because the derivative has relative extrema. This means if the derivative had a relative extrema, that means its derivative must change signs. And anywhere the second derivative changes signs means you have a point of inflection on the original. So that's what we know about f based on f prime. What do we know about the second derivative based on f prime? We have the graph of f prime. What does that tell us about f double prime? We know the second derivative changes from negative to positive at x equals 2 because the derivative has a relative minimum. So now we're back to, I know we're talking about the second derivative, but since we have the first derivative, we're really just talking about a function and its derivative. All right, my derivative here, f prime, is my function, and f double prime is its derivative. So I know that when a function has a relative minimum, like say at 2, I know that its derivative must change from negative to positive. All right, so that's how we come to that conclusion. Similarly, the second derivative here changes from positive to negative at x equals negative 1 because f prime of x has a relative maximum. So same idea. I'm not going to explain it again. It's just the vice versa idea. We know that the second derivative is negative on the interval negative 1 to 2 because the derivative is decreasing. Again, that's just the relationship between a function and its derivative. Wherever this function is decreasing, its derivative must be negative. So that's why we know the second derivative is negative, because the derivative is decreasing. Similarly, we know when the second derivative is positive. Because the derivative is increasing on those intervals, okay? Oh, I forgot to mention, we also know that the second derivative is a quadratic with a positive coefficient. Because I'll say because the second derivative is a quadratic with a positive coefficient because f prime is a cubic with a positive coefficient. Let's look at our last example. Here's a graph of f double prime. What can we say about f and about f prime? First of all, we know, again, that this second derivative here is a cubic, and it's got an upward trend. It's got an end behavior of down, and then a right end behavior of up. So that upward trend means it's got a positive coefficient. So what can we say about f? We can say that f of x has a point of inflection at x equals 0 because f double prime of x changes sign. Right? We change from negative to positive here. So anytime the second derivative changes signs, f has a point of inflection. We don't care if it's like from positive to negative or negative to positive. They're still called points of inflection in either case. I don't change the name of them. F of x is concave up on the interval 0 to 3, union 3 to infinity, because the second derivative is positive. So anywhere your second derivative is above the x-axis or positive, we know the original function is concave up. We know that f of x is concave down on the interval negative infinity to 0 because the second derivative is negative. So anywhere the second derivative is below the x-axis, which is here, I know the original is concave down. We know, oh, I forgot, yeah, so f of x is a quintic, degree 5, with a positive coefficient because f double prime is a cubic function with a positive coefficient. Should say positive leading coefficient, sorry. So I need to say that up here as well, leading coefficient. All right, so what can we say about f prime based on the graph of f double prime? Well, we know that f prime is decreasing on negative infinity to 0 because the second derivative is negative. So anywhere where the second derivative is negative, we know the derivative should be decreasing. Again, that's that relationship between a function and its derivative. We know that the derivative is increasing on the interval 0 to 3 and also 3 to infinity because f double prime of x is bigger than 0 or positive. So anywhere that the second derivative is positive, we know f is increasing. We know the derivative has a relative minimum at x equals 0 because the second derivative changes from negative to positive. Right? we got a negative, and then it changes to a positive. That happens at 0. So we know that there's a relative minimum there. There is no relative maximum on the derivative because the second derivative never changes from positive to negative. We see that it just bounces here. So we don't know. There's no relative maximum. I guess we could list that as a thing that we know there's not a relative maximum, but we'll just won't put it on our list for now. Now, for some fun stuff, we could say the derivative has a point of inflection at x equals 1 and x equals 3 because the second derivative has relative extrema. And that means, just to say why you know that f prime has a point of inflection, f prime would have a point of inflection where f triple prime changes signs, and that's going to happen where f double prime has relative extrema. So we'll say, which means f triple prime changes signs. So we can kind of say the similar when it's concave up, and concave down now. So the first derivative here, f prime is concave up on these intervals because the second derivative is increasing. So that's negative infinity up to 1, and then again from 3 to infinity. So f prime is concave up on these intervals because the second derivative is increasing, and that really means that f triple prime is bigger than 0, right? Because if f double prime is increasing, f triple prime is bigger than 0. Anywhere where triple prime is bigger than 0, that means f prime would be concave up. And then we have the vice versa situation. So anywhere where second derivative is decreasing, f prime is concave down, and that's because really we know that f triple prime, I should say which means f triple prime is really negative. Because if f double prime is decreasing, I know f triple prime is negative. Anywhere f triple prime is negative, f prime should be concave down. Okay, now we've got, you'll see a couple calculator active questions. These are the second part of your homework. I'm going to check these for a 5-point assessment, and you need to explain your reasoning and stuff as well. Okay, not assessment, but a 5-point classwork grade. So you're not done here with the video. You're going to move on and do these calculator active questions. I want to see those when you come into class first thing for a 5-point check. See if you can answer some of these questions that might show up on an exam based on the information we just went over.